A small ember flickers at the edge of time. JADES-GS-z14-0 steps out of the dark with a clean hydrogen cliff, a blue continuum, and the first hints of oxygen at cosmic dawn. Massive newborn stars crowd a compact core. Shock fronts lace the gas. A local bubble clears a window through the early fog. Lines prepare to rise where instruments will soon listen. If oxygen is already here, the universe learns fast. Gravity compresses, cycles tighten, and the earliest furnaces begin to sing. The story opens now where ancient light becomes a map and the first metals write the rules. The James Webb Space Telescope turns a silent gold eye toward a small rectangle of sky, and in that patient stare a smudge of ancient starlight steps forward. Within the program known as the JWST Advanced Deep Extragalactic Survey, an object gains a name, JADES-GS-z14-0, and with the name comes a growing hush in the control rooms and data centers that nurse these observations into meaning. The near-infrared camera builds a map of light in several carefully chosen bands, each band a sieve for photons stretched thin by the universe's expansion. In these images, the object does not behave like nearby galaxies. It falls away to near invisibility in bluer bands, and then suddenly rises in redder bands as if stepping across a threshold only very distant light can cross. That step is the signature of the Lyman break, the place where intergalactic hydrogen drinks ultraviolet light and leaves a clean cliff in the spectrum. The cliff's position hints that this galaxy lives at a redshift of about 14 when the first few 100 million years have barely opened. The colours do more than place the object beyond a vast gulf of time. They whisper of lines of narrow spikes of emission that can brighten a filter beyond what a smooth continuum alone would allow. Astronomers have a habit of trusting both simplicity and doubt at once, and here the simple story would be a young galaxy with raw star formation, while the doubt leans in and asks why some filters seem unexpectedly strong. In the stacks of exposures, oxygen announces itself as a possibility before anyone dares to call it a fact. Doubly ionized oxygen born when hard ultraviolet light plucks away electrons in clouds around massive stars can pour energy into specific wavelengths that land squarely in the camera's most sensitive windows at this extreme distance. If that conjecture is true, then a metal, a product of stellar alchemy, is already present in quantities large enough to sculpt the observed colors. Metallicity, the share of elements heavier than hydrogen and helium, becomes the quiet antagonist of the scene. Standard stories teach that the first stars form from pristine gas, live brief and violent lives, and scatter the first heavy elements into their neighborhoods, after which later stars inherit that mixed material. Time is needed for this cycle to repeat and accumulate, yet the galaxy on the screen could be showing that time compressed, as if the cycle has spun once, and perhaps even twice before the universe has learned to walk. The field that holds this source is crowded with faint points and smears, many of them quiet and cool, some of them deceptive. Foreground galaxies can masquerade as ancient by arranging dust emission lines and odd shapes in misleading ways. The team begins the necessary rituals of doubt. They measure shapes with careful point spread functions, searching for hints of lensing or blended neighbours. They check for scattered light, for detector quirks, for subtle background gradients that might lean flux from one aperture into another. They rebuild the photometry with alternative pipelines, shaving uncertainties and asking whether the strange colours survive small stubborn changes in method. The object remains. It is compact and luminous for its age, a knot of star formation cradled in the earliest web of structure. Its silhouette suggests clumps within clumps, as if gravity is knitting together pieces that have barely had time to meet. The light that leaves those clumps carries more than position and brightness. It carries the history of stellar births and deaths encoded in faint modulations across the camera's bands. If oxygen is truly involved, then the knitting has pulled in threads from the first generation of supernovae, those titanic endings that sweep the gas with stone and ash and carve nests for later stars. The suspicion of oxygen does not come from a single number or a single plot. It arises from the way certain bands sit higher than their neighbours, even after careful modelling of the continuum. The team compares the data with libraries of model spectra that include and exclude strong lines. They slide redshifts, alter the mass of stars, steepen and flatten the continuum slope that dust and age can shape. The solutions that best fit the elevations in the flux tend to involve the fingerprints of oxygen blended with hydrogen recombination lines, all magnified by the unusual youth and intensity of the star-forming regions. The idea hardens into a working hypothesis. This galaxy is not only distant, it is already chemically active. The backdrop to this inference is the reionization era, a time when the first galaxies send out enough energetic photons to tear electrons from hydrogen across great volumes, turning the fog of neutral gas into a thin, transparent medium. If the galaxy lives inside or near an ionized bubble, its light escapes more easily, and emission lines stand taller and cleaner against the cosmic dusk. The image of a bubble within which oxygen sings is appealing, almost cinematic, but the team resists romance and asks for proof. Imaging alone cannot end the argument. Yet imaging can choose the battlefield. The battlefield is the precise set of wavelengths where oxygen lines should fall at a redshift near 14 and where hydrogen features should keep them company. The team designs the upcoming spectra with the near-infrared spectrograph in mind, mapping shutter patterns, background levels, and integration times to catch the faintest possible spikes above the noise. Tonight, though the tale remains in the court of images, in that court the case for great distance is already strong. The absence of light in the bluest filters is like seeing a coastline retreat under a tide, and then the sudden rise in the redder filters is like watching a lighthouse emerge from fog. The bell of possibility rings in 3 places at once: an extreme distance, a burst of star formation, and the earliest appearance of oxygen that can be defended with data. Each bell carries a question. How did this object assemble so quickly, gathering enough fuel to shine so brightly in so little time? How did the first rounds of stellar birth and death proceed so efficiently that oxygen now lifts the flux in select filters? How many such sources wait unseen, their light too thin for even this telescope to catch, without long deliberate stares? The images deliver wonder with restraint. They show a point becoming a presence becoming a story about the first islands of starlight learning to enrich themselves, while the universe still yawns from its violent beginning. The team catalogues the object with a name, logs it into databases, flags it for immediate spectroscopic follow-up, and then returns to the images once more, because the colours continue to hint at something that might rewrite the earliest chapter of chemical history. The galaxy sits there, a message written in stretched light, and the message seems to say that oxygen arrives not late but early, and that the universe does not always wait for comfort before revealing its ambition. Word count 930. Awaiting continue. The images that first revealed the distant galaxy now become a laboratory, where colour alone carries the weight of inference. Astronomers within the James Webb Space Telescope Advanced Deep Extragalactic Survey combine near-infrared camera filters so that each window favours light stretched from ultraviolet into deep infrared. A young galaxy at a redshift near 14 should fall away in bluer bands, where intergalactic hydrogen absorbs, and then rise in redder bands where the absorbed light returns. This drop and rise outline appears, yet the team searches for more excess brightness in selected red filters that a smooth continuum cannot explain. Such excess hints at emission lines, narrow peaks borne in gas around massive stars. In a universe this young, the most telling candidate is doubly ionized oxygen, which thrives when radiation is both intense and hard. Color indices are built to test this pairing filters so that one traces the continuum while another is poised to be lifted by a line. They do not rely on a single pairing. A mesh of comparisons checks whether the object rises against its own baseline in multiple adjacent windows. Noise may forge a single jump, but it rarely paints a consistent pattern. Photometry is refined with apertures matched to the point, spread function. Backgrounds are subtracted with care to avoid faint neighbors, and bias is hunted by repeating the measurements with altered assumptions. In these trials, trust gathers slowly. For JADES-GS-z14-0, the colors carve the expected cliff and plateau, and then they show extra lift where doubly ionized oxygen would fall. The intuition becomes quantitative. The measured fluxes are compared to libraries of model spectra with varied star formation histories, stellar masses, and nebular emission across metallicities. Metallicity. The fraction of elements heavier than hydrogen and helium acts like a dimmer for line strength. Purely pristine gas struggles to match the elevations without an implausibly hard field, while a modest amount of oxygen reconciles the pattern with vigorous yet reasonable young stars. Still, the danger of foreground imposters remains. A nearby emission line galaxy can feign the same color tricks if a strong line lands in a red filter while dust hides blue light. The team counters by examining morphology. The source is compact and nearly symmetric with no clear arcs or duplicates that would betray gravitational lensing. Its surface brightness profile fits a small bright knot, rather than a blended or stretched system. Methods that estimate photometric redshift are then applied using different templates and priors. The solutions cluster at very high redshift, and the low redshift alternatives require dust and line combinations at odds with the measured continuum slope. Thus, the color case converges a dropout that marks the hydrogen break, followed by elevated points that argue for early oxygen. Color is persuasive but fallible, so it now shapes the spectroscopic plan. It indicates which wavelengths deserve attention, how long to integrate, and how to place the micro-shutters of the near-infrared spectrograph to avoid contaminants. Expected wavelengths of hydrogen features and of doubly ionized oxygen are mapped against instrument behavior so that the shutters open where the signal most likely hides. In parallel, the color inference is stressed by varying assumptions about stellar populations and gas. If the stars are unusually massive and short, the radiation field becomes harder, strengthening oxygen without very high metallicity. If the gas is dense and clumpy, collisional processes and young supernova remnants can amplify the lines. Both routes move models toward the data, yet each implies a different pace for the first cycles of birth and death. Dust adds another thread. The continuum slope looks very blue, arguing for little dust, and yet the lines appear large, a combination that elsewhere often pairs with dusty star-forming pockets. If dust is scarce, then photons escape more easily, raising the observed line contrast. That would fit a setting in which the galaxy sits inside a small ionized bubble in the wider sea of neutral hydrogen. No single inference settles the issue, but together they sketch a scene in which oxygen arises earlier than comfortable models predict. The implication is provocative. Either the first stellar generations enrich their surroundings at a pace that compresses cosmic time, or the masses of early stars are tilted toward the most massive, or both. With more massive stars, supernovae arrive quickly, pouring oxygen into the gas and lighting it with strong lines. A subtler bias could hide in calibration. Photometric 0 points drift with time and field position, and backgrounds vary so the team audits every step. Elevated filters are tested to see whether they remain elevated under reasonable choices. They do. The colours hold like a chord, and the chord carries a tone that sounds like oxygen. The weight of evidence moves from suspicion to intent. Spectroscopic observations are scheduled, instruments are tuned, and the shutters will open on the precise set of wavelengths that colour has marked. In the meantime, colour continues its quiet work, telling a story, with restraint and a hint of mischief keeping unresolved the tension between simple youth and surprising chemical maturity. The object holds steady in the data compact and bright for its age, and its colours keep pointing to chemical work already underway. Patience will turn these hints into measures and measures into the first firm steps toward a timeline of oxygen at cosmic dawn. The spectroscopic night arrives with a plan carved from colour. The near-infrared spectrograph of the James Webb Space Telescope opens its microshutters in a pattern tuned to the position of JADES-GS-z14-0, leaving neighbouring shutters to sample the background and to guard against scattered light. The field is nodded and dithered so that the object's faint trace walks across the detector in a way that breaks any single pixel's power to mislead. Calibration lamps and reference stars set the wavelength scale, and the flux response and daytime rehearsals become a memory against which the raw stream of photons is now judged. The team expects that at a redshift near 14, the strongest guidance will not be a towering emission line but a cliff. A sudden suppression of the continuum where intergalactic hydrogen devours ultraviolet light. That break should fall near 1 1/3 microns for the hydrogen edge, and near 1 4/5 microns for the hydrogen Lyman alpha line, and the spectrograph is by design most reliable in precisely this terrain. The shutters remain open for long integrations measured in many thousands of seconds, because the signal is thin while the stakes are high. Even as exposures accumulate, the reduction pipeline treats each frame as a delicate object. Dark current is measured and removed. Cosmic rays are identified and rejected. The shape of the instrument's sensitivity is tracked across time, and the two-dimensional trail of the spectrum is traced and extracted into a one-dimensional line that carries flux against wavelength. The team resists the first thrill of a feature until the same feature survives independent paths of analysis. A slope appears and then falters sharply at the expected position of the hydrogen break. The continuum is present redwood of the break faint but coherent, and it is absent bluewood holding to a near zero level within the uncertainties. This is the signature that imaging anticipated and that spectra can now show with higher authority. The hydrogen Lyman alpha line in a universe still thick with neutral gas is not expected to blaze. In the extracted spectrum it remains quiet perhaps, with a softness just redwood of the line, where a damping wing might be whispering of neutral hydrogen around the galaxy, but the evidence remains cautious. The absence of a strong Lyman alpha line does not weaken the case for distance. At this epoch, it is more a sign of context than a failing of the source. The spectrograph also listens for any bright imposter features that a low redshift galaxy could cast into these wavelengths, but such lines do not materialize. No obvious oxygen from a nearby system, no neon, no sulfur at the wrong place and scale. The spectrum stays clean in the sense that it is not cluttered with low redshift tricks, and it is rich in the sense that the continuum and the break together tighten the redshift solution. A photometric redshift becomes a spectroscopic redshift, and the uncertainty narrows from a broad plateau to a confident ridge. With distance in hand, attention returns to the puzzle that drove the observations. At a redshift near 14, the familiar oxygen lines that often blaze in nearby star-forming galaxies would be shifted into the mid-infrared beyond the upper reach of this instrument. Their absence from the spectrum is therefore not a verdict about chemistry, but a reminder of physics. The photometric hints of oxygen strength live in the way broad filters were elevated by lines now moved to wavelengths that the near-infrared spectrograph cannot collect. The team reads this as a map for what must come next rather than as a contradiction. The spectroscopic confirmation of distance tells them that the earlier colour inferences were made at the correct cosmic scale. Now they test the spectrum for more subtle signs of the engine behind those inferences. The continuum slope redwood of the break is very blue, which means that the light falls away at longer wavelengths as expected for a very young stellar population with little dust. That same scarcity of dust would let ionizing photons fly farther, carving channels that encourage emission lines in surrounding gas. The lines themselves remain out of reach here, but their likely strength is consistent with a hard radiation field and with the quick birth and death cycle that would plant oxygen so early. The team quantifies this consistency. They fit the spectrum and the imaging, simultaneously joining the precise placement of the break with the measured photometric elevations. Stellar population models accommodate the blue slope with a burst less than a few tens of millions of years old, while the line strengths implied by the photometry require either a compact and intensely star-forming region or a stellar population skewed toward the most massive stars. Both pictures agree that time has been compressed, that a few generations of massive stars could already have lived, died, and enriched the gas. They test the robustness of the redshift against every nuisance they know. They allow for sky-like background ripples even though space has no atmosphere. They shift extraction apertures wider and narrower. They change polynomial orders in baseline fits. The break persists. Independent teams take the same data and rebuild the spectrum with their own software and their own habits of caution. The answer does not change. A galaxy at a redshift near 14 sits in the spectrograph, its light shaped by intergalactic hydrogen and by youth. With the distance locked, the oxygen question sharpens into a plan for complementary observations. The mid-infrared instrument can in principle catch the doubly ionized oxygen complex and the hydrogen beta line at these stretched wavelengths, though the required exposures are formidable. The Atacama Large Millimeter Array can search for far infrared cooling lines and for dust that may betray hidden processes even when the continuum appears clean. If those efforts succeed, they will put the chemical fingerprint directly on the spectrum. For now, the spectrum has done a different but essential job. It has fixed the coordinate in time, letting all later measurements hang on a precise redshift. It has excluded a family of low redshift imposters and has shown a continuum and a cliff that are emotionally austere but scientifically generous. The galaxy speaks softly, yet what it says is strong. It lives when the universe is only a few 100 million years old. It shines with a blue continuum that tells of short-lived stars. Its colours still insist on emission lines that this instrument cannot see, but that other instruments may find. The team closes this phase knowing that the door to oxygen is now truly ajar. The line between suspicion and measure has brightened, and the next campaigns will decide whether oxygen's early arrival is a rare accident or a common feature of the first islands of light. The confirmation of distance sharpens the next task into one of disciplined doubt, because any claim of early oxygen must first survive the full parade of imposters. The team begins with the most common masquerade, a nearby galaxy, whose rest frame optical lines are so powerful that they inflate one or more red filters and mimic the color jumps of extreme distance. They construct templates of such interlopers with strong oxygen and hydrogen beta lines and dust that erases blue light, and they force these templates through the same filters used by the near-infrared camera. The fits stumble on the continuum slope, which for the distant source is very blue, while the low redshift solutions require both dust reddening and contrived line ratios to keep pace with the measured points. A second imposter follows close behind a galaxy at intermediate distance with a pronounced break from aged stars that pretends to be the hydrogen break. The team tests this by tying the photometry to stellar population models with long calm histories and by requiring that the mass and size match the compact form seen in the images. The result is tension that refuses to relax. The distant solution uses youth and a clean break in intergalactic hydrogen to explain the fall in blue filters, while the nearby solution must juggle an old stellar population dust and a surface brightness too high for its proposed distance and size. Lensing is next because a mild magnification could brighten a faint intruder and bend its colours through subtle blending. The team hunts for evidence of gravitational lensing by charting the shapes and orientations of faint neighbours, and by searching for mirrored structures or thin arcs. They fit simple lens models to the foreground catalogue and ask whether any mass concentration can produce a single, bright image without obvious companions. The models return small magnifications at most with no pattern of shear around the source. The light profile of the object remains compact and symmetric, and there is no second image where a lens would demand one. Thus, lensing cannot rescue low redshift alternatives, and it is unlikely to be the reason for the object's prominence. Instrumental ghosts and artifacts take their turn under the lamp. The micro-shutter array of the near-infrared spectrograph is checked for light leaks and for scattered light from bright sources outside the grid. The dither pattern ensures that any residual does not sit at a fixed position on the detector. The reduction pipeline marks frames for latent images and persistence, and discards any with elevated backgrounds that do not track the source. Flat field maps and bad pixel masks are used to scrub small-scale calibration scars, and independent teams apply their own calibrations to ensure that no shared oversight survives across reductions. The features that signify distance remain in the spectrum after all of these purges. If the spectral cliff is genuine, could the colours still be built by a foreground object blended with a high redshift neighbour? Deconvolution tests address this by fitting the point spread function to the source and to its immediate surroundings with multiple shapes and sizes. Residual maps show no hidden companions within the beam that could skew the photometry. Apertures are grown and shrunk, elliptical masks are rotated, and the flux in elevated filters does not depend on such choices beyond the trusted uncertainties. Forward modelling then takes the whole process and runs it from sky to catalogue. Synthetic sources are injected into the raw frames with chosen redshift sizes and spectra that include or exclude strong lines. These synthetic skies pass through the same detection and measurement pipeline, and the recovered colours are compared to the real object. Only the models that place the source at very high redshift with modest oxygen enrichment reproduce both the blue continuum and the boosted filters without introducing inconsistencies elsewhere. Those models do not prove the reality of oxygen. They demonstrate that the pathway from true sky to measured numbers does not itself manufacture the signal. A more exotic imposter is a cool dwarf star in the Milky Way, whose molecular bands can mimic a drop and rise when viewed through the wrong filters. The team tests this by examining the shape and compactness of the source and by comparing its colours with libraries of brown dwarfs. The The source is too blue and too steady in its continuum to be a cool dwarf, and its minimal elongation across dithers argues that it is not a star that wandered through multiple sub-pixel phases. The possibility that a noisy background or a fluke alignment lifts certain filters more than others is addressed by building many noise realizations over the local background and repeating the measurements. The elevated points persist above the tail of statistical accidents. Another suspicion focuses on calibration drifts the tiny shifts in photometric 0 points across the field or between observing visits. The team audits the standard stars in the field, recalibrates the 0 points, and propagates those changes through the catalogue. The 0-point adjustments are too small to erase the excesses, and in some reductions the elevations grow slightly stronger when the newest calibrations are used. The most stubborn imposter is a blended low redshift emission line system hiding below the detection threshold in some bands. High-resolution imaging helps here. The object remains a single compact source with a profile consistent with a small galaxy at great distance rather than a composite of multiple knots at modest distance. Cross-checks with catalogues from other deep programs find no catalogued foreground sources at the same position. The final battery of tests is conceptual rather than technical. The team asks what kind of star formation and gas conditions would be needed to generate the implied oxygen strength if the distance is correct, and whether those conditions would violate other constraints. They find that a very young, dense star-forming region with a radiation field dominated by massive stars can in principle power the needed line strengths while keeping the continuum blue. That setting also explains the relative absence of dust and the potential for a local ionized bubble that lets photons escape. These combined inferences do not remove doubt. They localize it. Doubt no longer lives in the suspicion of a masquerade. It moves into the physics of the source itself. The competing picture in which the source is a nearby mimic fades as each test removes a prop. The spectroscopic break argues for great distance. The morphology argues against lensing tricks. The photometric stability argues against calibration ghosts. The simulations argue that the pipeline does not forge the signal. Agreement across independent reductions argues that individual habits and choices are not the culprit. The oxygen story grows heavier not with certainty, but with the absence of credible alternatives. That absence does not make the early arrival of oxygen ordinary. It makes it urgent. If these features are real, then enrichment has begun with startling speed, and the models that describe the first cycles of star birth and death must stretch. The team writes this into their plan for the next campaigns. They will seek the lines directly with the mid-infrared instrument where the wavelengths now live. They will use the Atacama Large Millimeter Array to search for complementary cooling lines and faint dust. They will widen the search to similar color-selected sources to learn whether this is a lonely outlier or the first of many. For now, imposters have had their say and have fallen quiet. What remains is a compact blue galaxy at an enormous redshift with colors that continue to suggest that oxygen has already left fingerprints on the ancient light. The mystery is not whether the signal exists. The mystery is how the earliest engines made it so quickly and with such strength. Deep imaging now takes the lead because structure can reveal how a tiny galaxy makes oxygen so quickly. The near-infrared camera stacks many visits into a clean portrait, and within that portrait JADES-GS-z14-0 appears compact, bright and slightly irregular. The measured light profile is small, likely only a few hundred parsecs across at the measured distance, a scale that elsewhere hosts a single giant star-forming complex rather than a settled disk. The radial curve is steeper than a calm disk, yet broader than a point which signals clumps packed into a tight core where gravity is strong and time runs fast. At these wavelengths, the rest frame ultraviolet becomes infrared, so each bright knot traces very young stars that heat and strip their surrounding gas. Two-dimensional fits allow asymmetry and substructure, and the best solutions prefer a bright central knot with a faint extension, a head, and a thin tail that could be a minor companion or a wake carved by feedback. Residual images after subtracting smooth models show small ripples that match clustered star formation, many sparks igniting together. Clustering matters because clustered stars share radiation, and supernova shocks pushing ionization to extremes, and naturally raising oxygen lines even when dust is scarce and the continuum stays blue. A color map across the source shows the core with the bluest slope, and only a gentle reddening outward a uniform youth that argues against complex dust geometry. Such uniformity is rare at later times, and supports a picture in which the whole system has only just switched on. Combining total light with size yields a high star formation, surface density the kind seen in intense starbursts, even if the total mass is modest. In such regimes, gas does not drift into stars. It plunges, and the most massive stars form in crowds, live for only a few million years, and explode, throwing oxygen into the surrounding gas both locally and globally. Where clumps sit close together, the resulting shocks and pressure overlap, stirring the gas and shortening the time between enrichment and the next round of starbirth. This overlap is central to any story that places oxygen this early, because it converts a sequence into a closed loop that runs quickly. The faint extension hints that inflow is still feeding the core. It could be a thin stream of gas falling inward, tidally stretched by the young potential, or a small satellite under disruption. Either way, fresh fuel sustains the knots, hardens the radiation field, and keeps the future emission lines high. The data are split by visit and orientation to test stability. The bright core remains bright, and the extension keeps the same angle and scale, which shows that the features are not artifacts of a single sequence. Point spread function fits with nearby stars confirm that the source is truly resolved and the size is intrinsic. With that reassurance, the team asks whether a system so small can already drive outflows that carry oxygen into its halo. Direct proof awaits resolved spectra, yet the combination of high surface brightness, blue continuum, and clumpy structure is a known signature of winds in later epochs. If winds are present here, they would cut low-density channels that let ionizing photons escape, boosting line contrast and helping a local ionized bubble open within the wider neutral sea. Such a bubble would make any oxygen lines easier to detect at the correct wavelengths. Comparisons with simulations of early assembly are instructive. Models with cold streams, rapid cooling, and bursty star formation often build compact head-tail starbursts at very high redshift. In those models, the first supernova enriched the gas within a few tens of millions of years, and clustered feedback mixes the metals across the tiny system quickly. The observed morphology matches that pattern closely enough to lend plausibility without claiming proof. Alternatives that would reduce the need for early enrichment, such as a dusty foreground interloper blended with a blue background source, predict lopsided light or strong color gradients that are not seen. The clean, nearly symmetric core with only a mild extension keeps alive the simpler reading of very young galaxy, forming stars at a ferocious rate and already bearing their chemical marks. The team also checks whether emission lines inside the imaging bands could bias the size upward by brightening specific regions. They fit sizes in filters where line contribution should be lower based on the measured redshift, and find that the compact size remains, which argues that the map traces starlight rather than line-dominated patches. Within that map, the central knot dominates, pointing to a peak in density, where the most massive stars crowd, and where their deaths concede oxygen with speed. The faint outer glow may already be receiving that material, either as a fine mist from overlapping winds or as denser shells from recent explosions. If the latter is true, the system could be caught in a phase where enrichment and new star formation alternate at scales too small to resolve turning chemical evolution into fast motion. Imaging alone cannot weigh the gas or time the winds, but it fixes the stage with firm facts. The galaxy is very small for its brightness, and visibly clumpy, which together shout youth and pressure. It is not a smooth ball of old stars. It is a ragged ember whose edges are still being blown by the winds it makes. From this form, the oxygen hypothesis gains a physical home. If later spectra confirm strong oxygen lines, they will have been forged in these very knots and carried outward by the same forces that carved the faint tail. The next campaigns will try to listen to those knots directly with the mid-infrared instrument and with the Atacama Large Millimeter Array, but for now the map of light already says that the furnace is lit. Every pixel becomes a fragment of a story that began when the universe was still assembling the first scaffolds, and the story it tells is simple and odd at once. Simple because compact, clumpy starbursts are efficient factories for oxygen. Odd because such a factory is already running when the universe is only a few 100 million years old. The picture therefore works as both a map and a challenge, a map of what is present, and a challenge to the timescales that many models have expected. The galaxy does not look patient. It looks urgent, and oxygen thrives on urgency. The question now tightens around the engine that can drive such strong ionization in so small and so young a system. The imaging and the spectroscopic break have fixed the distance and the youth. What remains is to weigh the hardness of the radiation field, the density of the gas, and the ease with which energetic photons escape. The combination of a very blue continuum and elevated flux in filters, likely boosted by lines, argues for a radiation field crowded with the most massive short-lived stars. Such stars pour out ultraviolet light hard enough to strip 2 electrons from oxygen, creating the doubly ionized state that radiates so brightly in familiar nearby galaxies. At this distance, the traditional oxygen lines fall at mid-infrared wavelengths, but their fingerprints are already implied by color. To sharpen the picture, the team builds models that link line ratios to the physical conditions in the star-forming knots. They track the ratio of doubly ionized oxygen to hydrogen beta as a marker of hardness, and the ratio of doubly ionized oxygen to singly ionized oxygen as a gauge of the ionization parameter, which is the density of ionizing photons relative to gas density. They find that only an intense source can lift these ratios to the heights required by the photometric excesses without draping the continuum in dust. Massive stars provide such intensity, and if the earlier stellar population is skewed toward very high masses, the effect strengthens. A top-heavy distribution shortens the time from birth to the first supernovae, both hardening the light and planting oxygen in the gas. Electron temperature and electron density also matter. Low metallicity gas cools poorly because it has few lines to carry energy away, so electron temperatures rise, and higher temperatures make the collisionally excited oxygen lines more luminous for a given abundance. If the gas is also dense in the knots, collisional processes increase the rate at which electrons bump the ions into excited states that shed energy at distinct wavelengths. These conditions are not exotic at early times. They are the natural outcome of rapid collapse and clustered star formation inside a small gravitational well. Such clusters carve Strömgren zones, spheres where hydrogen is fully ionized, and where the radiation propagates through lower opacity channels. In that setting, photons with enough energy to ionize hydrogen can reach larger volumes than in a dusty, placid galaxy lifting line strengths, and creating a steeper ionization gradient within the small system. The team tests how much photon escape is needed to make the observed pattern. A high escape fraction lets many ionizing photons leave the galaxy, entirely softening the local nebular glow, but it also carves channels that can amplify the contrast of the lines that remain by lowering the continuum absorption and boosting the visibility of bright pockets. Simulations suggest a middle ground where overlapping winds and cavities let hard light leak, while still preserving dense clumps that shine with strong lines. In such a setting, a small ionized bubble surrounding the galaxy can form, and that bubble helps the faint continuum survive intergalactic absorption, while letting potential emission lines stand taller against the cosmic fog. The interplay between hardness and metallicity becomes a fulcrum for interpretation. With very low metallicity, the continuum stays blue, and the radiation is hard, yet the absolute abundance of oxygen is small. With modest metallicity, the abundance rises, and with it the potential line strength, but the stars may cool a little, and the continuum may redden. The colours of JADES-GS-z14-0 favour the first trend in the continuum and the second trend in the lines, a combination that points to a narrow window where enrichment has begun but has not yet softened the engine. In that window, the electron temperature stays high and the line emissivity per atom is large, while the total number of oxygen atoms is no longer negligible. This is one way to compress time and let a few cycles of massive star birth and death quickly enrich a compact region, while the broader population still looks barely older than newborn. The team also explores the possibility that shocks from supernova remnants contribute to the ionization budget. In the first few million years after the first explosion, shock fronts run through the surrounding gas, heating and ionizing it, with a spectrum that can mimic or exceed the hardness of young stars. Shock models added to the stellar models can raise doubly ionized oxygen relative to hydrogen lines without invoking extreme stellar assumptions. The cost is that shocks often broaden lines and alter ratios of other species in ways that future spectra will need to test. If shocks matter here, they could also explain a faint tail structure as the visible wake of energy pouring through the small system. A final ingredient is geometry. Ionization fronts wrap around clumps and shadowed pockets can stay neutral, while exposed faces blaze. Even at a single metallicity and a single average density geometry can produce a mosaic of conditions that together resemble a harder source. This matters for the reading of colours because an unresolved mix of hot faces and cooler interiors can boost specific bands more than others. The team creates toy geometries and finds that compact clusters embedded in porous gas can reproduce the extreme line to continuum contrast inferred from the imaging. Each of these routes shares a theme. None require a hidden massive black hole or an exotic physical law. A dense, compact starburst with very young age, modest early enrichment, high electron temperature, and a porous interstellar medium can explain the necessary line power. The uneasy part is not the mechanism, but the schedule. All of this must happen when the universe is only a few 100 million years old. That schedule pushes on models of how fast gas collects, how quickly stars form, and how much of that light and energy escapes. If the engine in this galaxy is typical, then early enrichment and strong ionization may be common. That would help explain how the universe moves from neutral to ionized, so rapidly filling the cosmic web with transparent corridors earlier than some histories prefer. If the engine is rare, then this source becomes a laboratory for the extreme edge, a place where the first factories of oxygen reveal their rules at maximum speed. The next observations aim to distinguish among these engines by measuring the line ratios directly at mid-infrared wavelengths, and by probing far-infrared cooling lines and faint dust with ground-based arrays. For now, the models agree on a portrait clustered massive stars rooted in a compact knot, hard light flooding hot gas shock fronts, possibly adding their own sharpness, and a porous geometry that lets the energy reach far. The ionization engine is not a single machine but a small city of furnaces all burning at once in 1/4 kiloparsec. That city lights oxygen and sets the stage for the next step in the mystery, which is to follow the chemical fingerprints inward toward the gravitational heart. Metallicity now takes the stage as both measure and mystery, because the fraction of elements heavier than hydrogen and helium is the ledger that records how many stars have already lived and died. The colours and the spectrum together suggest that the galaxy glows with a very blue continuum, yet also shows elevated flux in bands likely touched by emission lines. This combination points to very low but not pristine metallicity, a state where the gas is still mostly primordial, yet already seasoned by the ash of the first short-lived giants. The team approaches the estimate with several lines of reasoning, each imperfect alone and stronger in company. They fit the joint imaging and spectroscopy, with libraries of model spectral energy distributions that include both stellar light and nebular emission, allowing star formation histories that rise quickly and then pause, and allowing metallicities that start near zero and creep upward. Solutions that match the very blue slope of the continuum demand dust to be scarce, and ages to be very young, while solutions that explain the flux lift in selected filters prefer some oxygen already present to power strong lines. When metallicity is set to nearly pristine values, the models can only lift the filters by invoking radiation fields so hard that they begin to conflict with the measured continuum shape. When metallicity is raised to modest values, the line power grows and the match improves without reddening the continuum beyond the observed slope. A second path relies on indirect line ratio proxies, inferred from the photometric pattern itself. The relative elevation of the filters that land on expected positions of hydrogen and oxygen, compared with the adjacent filters that likely trace pure continuum, constrains the plausible ratios of doubly ionized oxygen to hydrogen beta, and of doubly to singly ionized oxygen. While these are not measured directly at these wavelengths, the color architecture limits how large or small they can be. The allowed region on this proxy map rests where the oxygen to hydrogen ratio is not negligible, where electron temperatures are high, because cooling lines are still scarce, and where the ionization parameter is large because the young clusters flood the gas with hard light. A third path uses size and brightness to estimate a star formation's surface density and to connect that density to enrichment timescales. In galaxies at later times, the most intense compact starbursts can move metal content from very low to modest values in only a few tens of millions of years, because clustered supernovae seed and mix rapidly within small volumes. If JADES-GS-z14-0 occupies the same physical regime, then the timescale to reach a modest oxygen abundance is not extravagant despite the youth of the universe. The outlier requires not a new law but a compressed schedule and a compact stage. These routes meet at a point that is both satisfying and unsettling. They imply a metallicity that is low enough to keep the continuum very blue, and the electron temperature high, but high enough to fuel the oxygen lines that lift the photometry. That point arrives earlier than many histories prefer. The unsettling part is not that the value itself is impossible, it is that the path to it must be paved very quickly. The models answer with two families of solutions. In the first, the stars follow a normal distribution of masses, but the gas supply is high, the density is extreme, and star formation proceeds in a burst so concentrated that multiple generations of massive stars are born die and mix their yields into the next round in a compressed loop. In the second, the stellar mass distribution is tilted toward the most massive stars. That tilt shortens the time to the first supernovae and increases the share of oxygen in the yields, pushing the gas to modest metallicity even if the total star formation is similar. Both families permit the observed pattern. Both carry costs. The first demands an efficiency of conversion from gas to stars that strains comfortable limits, and an internal mixing speed that leaves little time for rest. The second demands an early environment that favours the birth of the very massive a preference that shifts the spectrum and the feedback in ways that future data must test. The team probes the edge of these costs. If the efficiency is high, then outflows driven by supernovae should appear quickly, perhaps carrying oxygen outward into a faint halo. That halo would alter the far infrared cooling lines and might leave a signature in the shape of the ultraviolet continuum through resonant scattering and subtle absorption. If the distribution of stellar masses is top-heavy, the continuum should be even bluer and harder than in the efficient but normal case, and the ratio of helium and nitrogen lines to hydrogen and oxygen should land in different neighborhoods once the mid-infrared instrument measures them. Dust threatens to confuse these signatures by changing slopes and hiding lines, but the current blue continuum argues that dust remains minimal, a condition that simplifies the reading. A further uncertainty lives in geometry and in time. Metallicity is not a single number everywhere. Clumps may reach modest oxygen content while the faint outskirts remain near pristine. Stars then form in gas that is unevenly seeded so that some pockets shine with strong lines while others contribute almost pure continuum. The integrated light of such a mosaic can mimic a uniform metallicity while holding a more complicated truth. Time adds another twist. If the starburst has only just turned on, the first supernovae may be imminent but not yet common, and the oxygen signature could rise further in a short cosmic moment. Conversely, if a brief earlier burst already seeded the core, the present burst could be lighting that enriched gas without adding much new metal, yet a two-step dance that compresses the visible signs into a single epoch. The team treats these uncertainties not as weaknesses but as maps for the next observations. Far infrared lines measured by the Atacama Large Millimeter Array can fix electron density and cooling channels. Mid-infrared lines measured by the mid-infrared instrument can separate the roles of radiation field and shocks. Together, these will pin the metallicity more directly and will tell whether the current inference sits on firm ground. For now, the estimate remains a well-supported assertion the galaxy is not pristine. Oxygen is present in amounts that matter, and those amounts have accumulated in a time so short that the phrase metal in minutes feels less like poetry and more like an honest summary. This matters beyond one object. If such metallicities are common at this epoch, then the early universe learns to enrich faster than many models assume, and the global march from neutral to ionized gas finds extra help from hotline bright pockets that are both engines and beacons. If rare, then this galaxy is a special window into an extreme mode that still must be understood, because extremes often write rules that the average hides. Either way, the message is clear. A compact galaxy at a redshift near 14 already carries oxygen, and the oxygen presses the clock of cosmic history forward by demanding early cycles of birth and death. The team closes this round of analysis with the metallicity number not as a trophy but as a question mark, a sign that the universe chooses speed when it could have chosen patience. dust now steps from the margins into the center of the frame because a grain of carbon or silicate can tilt a galaxy's entire face toward or away from visibility. The continuum of JADES-GS-z14-0 is very blue, a simple rise in brightness toward shorter rest frame ultraviolet wavelengths, and that slope is a first blunt test that dust is scarce. In a dusty galaxy, the powder of shattered stars reddens the light scattering and absorbing the shortest wavelengths and softening the climb. Here the climb holds, and it holds across visits, orientations and reductions. The simplest reading is that the small system is nearly dust-free, and yet the same data suggests strong emission lines that often coexist with at least some dust elsewhere. The team examines this tension by fitting the joint photometry and spectrum with attenuation curves that tell how dust dims light of different wavelengths. Classical recipes built from later galaxies lean towards stronger ultraviolet suppression than the data allow. Flatter curves that dim less in the ultraviolet fit more readily, but they remain consistent with only a very small amount of dust. This conclusion repeats under different star formation histories, metallicities, and ionization parameters. The continuum wants to stay blue. The line excess wants to stay large. Both can be true if the dust mass is tiny, the geometry porous and the star-forming knots crowded so that the line-emitting regions shine through low opacity corridors. This geometry arises naturally when clustered feedback carves cavities within a thin interstellar medium. Dust is more than an obstacle to light. It is a record of past stars. Grains grow in the winds of dying giants and in the ejecta of supernovae. In later epochs, slow growth in dense clouds adds mantles, building larger grains over time. At a redshift near 14 time itself is a stingy resource. The first generation of stars ends in a few million years, and their explosions can inject dust seeds quickly. However, those same explosions also shock and shatter grains. Whether a compact galaxy can build and keep dust in such a turbulent setting is an open question. The current blue slope argues that little has been kept. If dust is scarce, then why are the emission lines implied by the photometry so strong? One answer is that fewer grains mean fewer places for photons to die so hard. Radiation travels farther and ionizes more of the surrounding gas, raising the contrast of lines against a clean continuum. Another answer is that the electron temperature in low metallicity gas is high, because metals that usually cool the plasma are rare, and higher temperatures boost the collisionally excited lines for a given elemental abundance. Both effects lift oxygen without leaning on dust. The team probes the possibility that a small amount of dust is present, but arranged in patches that hide little of the ultraviolet continuum while reshaping the nebular glow. Such patchy dust can live in dense clumps that occupy a small fraction of the volume. If line photons must cross only short distances within these clumps before escaping into low opacity channels, they can survive. The integrated light then shows strong lines and a blue continuum at once. This picture gains plausibility from the compact clumpy morphology measured in the images. The starburst looks like a city of bright quarters separated by faint alleys, a plan that supports both high radiation density and short paths to freedom. Observations beyond the near-infrared provide listening posts for dust. Far infrared continuum from cold grains would betray even small masses if grains are warmed by the intense radiation of the core. The Atacama Large Millimeter Array seeks this glow and finds only upper limits, so far limits that restrain but do not extinguish the allowed dust mass. Those same observations can listen for cooling lines such as singly ionized carbon in the far infrared, which carry energy away from gas mixed with dust. Non-detections narrow the models toward hotter, more tenuous or less enriched gas, any of which reduces the expected far-infrared emission, while keeping the possibility of bright mid-infrared oxygen lines alive. The team folds these limits back into the spectral energy distribution fits, and finds that they favour low dust both in mass and in effective optical depth. Another route to dust is the shape of the continuum itself across the multiple near-infrared filters. Even when grains are scarce, their presence can curve the spectrum in a way that a dust-free stellar population cannot mimic easily. The measured continuum is consistent with a very young burst of low metallicity and only a whisper of attenuation. A small amount of nebular continuum can add smooth power without reddening the slope beyond the observed values. Together, these ingredients keep the narrative of scarce dust intact. If dust is truly this low, the reionization context shifts from a misted room to a set of open windows. Ionizing photons can escape more readily along the channels, carved by clustered winds, contributing to a local ionized bubble that thins the neutral fog around the galaxy. That bubble in turn reduces the damping of hydrogen features and eases the passage of line photons into space. The system becomes both a factory and a lighthouse, making oxygen and projecting its signal outward with minimal losses. A contrary concern remains. If grains are too few to hide light, are they also too few to seed molecules that cool gas and sustain further star formation? In dense pockets, even tiny dust fractions can catalyze molecules and help gas collapse. The observed clumpiness and the high star formation surface density argue that the system is not starved of such catalysts at the scales that matter most. The dust that exists may be young and small, built in supernova ejecta rather than in long-lived gentle envelopes, but it is sufficient to assist collapse while failing to extinguish light. A related test awaits the mid-infrared instrument. Hot dust close to the clusters can glow in the mid-infrared, and even a small mass can reveal itself through a gentle rise beyond the near-infrared bands. If such a rise is absent, it will strengthen the case for a nearly dust-free system, and push the models toward even higher electron temperatures and harder radiation fields to explain the line strengths. If present, it will argue for small hot grains that survive near the furnaces, a detail that would tighten the geometry and the energy budget. The dust story does not end with a count of grains. It opens into dynamics. Grains ride winds and trace flows. If a faint tail marks outflow dust within that wake, could be the first chemical export from the galaxy, a signal that enrichment is not only swift but mobile. Such motion would seed the surrounding medium and could plant future sites of star formation beyond the tiny core. For now, the evidence aligns to a common refrain. The galaxy is blue in its continuum, strong in its lines, and faint in any far-infrared whisper. This triad paints a picture of a newborn system where dust has barely begun to gather, where the paths for ultraviolet and ionizing photons are remarkably clear, and where oxygen lights the gas with little hindrance. The grains that do exist likely live in small, hot and patchy pockets, shaped by clustered star formation and rapid feedback. In such a place, the early universe looks transparent from within, and the chemical beacons travel far. The next step is to ask how those beacons move, how fast their carriers fly, and whether the compact knots are already stirring winds that will lift oxygen into a halo still too faint to see. The story now pivots to motion because the way gas moves decides how quickly oxygen spreads and how brightly lines will sing. Even without direct access to the classic oxygen features at these stretched wavelengths, dynamics can be read from the shape of the continuum, the compact size, and the energy that young stars must be pouring into their surroundings. In a system only a few hundred parsecs across, clustered supernovae and stellar winds rarely act alone. Their shock fronts overlap and their hot bubbles merge into a pressurized interior that pushes outward on every weak seam. The images show a compact bright head with a faint tail, a geometry that hints at preferred directions for flow, as if the infant galaxy has already found the path of least resistance and begun to exhale. The pressure source is straightforward. Massive stars inject momentum and heat at a rate that scales with the star formation's surface density, and in this object that density is high. The continuum's very blue slope testifies to a dominant population of short-lived giants and to a scarcity of dust, so that a large fraction of the mechanical energy converts into motion rather than into heating and hiding grains. Theoretical scalings borrowed from later compact starbursts suggest that the resulting wind speed can reach hundreds of kilometers per second in the frame of the small galaxy, easily enough to carry newly made oxygen beyond the central knots within a few million years. If these numbers hold, the first rounds of enrichment would not remain local. They would smear outward into a halo whose faint light the current data cannot resolve, but whose physical effect is immediate. A lower density exterior helps ionizing photons travel, easing the birth of a local ionized bubble within the wider neutral sea. That bubble makes it less likely for ultraviolet lines to be quenched, and more likely for mid-infrared oxygen to reach the telescope once observed. The team checks whether any spectroscopic hints of motion already exist in the present data. The extracted continuum is faint but real redwood of the hydrogen break, and weak undulations that might betray absorption or emission blends appear at the threshold of a confidence. Their shapes are not yet secure enough to claim a symmetry, yet they steer models towards scenarios where the gas is not at rest. If a damping wing is present just redward of the hydrogen Lyman alpha position, as some reductions timidly suggest it may be telling of neutral hydrogen around the galaxy and of outflowing gas that shifts the effective line edge. Whether or not that whisper holds the broader evidence supports a dynamic medium. Compact clumpy structure, high surface brightness, and a very young age are an alliance that elsewhere almost always breeds winds. The energy budget is probed in two steps. First, the total luminosity in the rest frame ultraviolet gives a star formation rate that, combined with size, yields the pressure and momentum input. Second, the inferred line strengths from photometry, if they hold, place the gas in a regime where electron temperatures are high and cooling is efficient through selected channels, so that a portion of the injected energy must be vented as kinetic motion rather than as radiation. If outflows are present, they will alter both the escape fraction of ionizing photons and the mix of line ratios by carving channels and by shocking pockets of gas. Shocks are double agents here. They can excite oxygen directly, but they can also push gas to densities and temperatures that quench some lines while strengthening others. The net effect depends on geometry and timing. A newly launched wind encounters the densest clumps first. It wraps around them, accelerates along low-density paths, and tears holes in places where previous supernovae left the gas thin. In that patchwork line, emission becomes angularly structured, and an unresolved observation integrates a kaleidoscope of conditions into a single spectrum. That integration can mimic an ultra-hard source, even without an exotic engine, precisely because the hottest faces of clumps dominate the light. The faint tail seen in the images could be the visible residue of such flow. If so, it might be composed of gas pushed outward and of small stars formed in compressed shells at the wind's leading edge. Those stars would be young and blue, helping the tail keep a similar continuum slope to the head while contributing little mass. The ratio of head-to-tail brightness places the flow in an early stage with most of the energy still concentrated in the core. As the flow matures, the tail would lengthen and thicken, and the halo would brighten in far infrared cooling lines that the Atacama Large Millimeter Array could one day detect. In the meantime, other dynamic fingerprints lie within reach. The mid-infrared instrument can, with audacious exposure times, measure the widths of hydrogen beta and of the doubly ionized oxygen complex at these redshifts. Line widths carry the sum of turbulence, thermal motion, and bulk flows. A narrow core with broad wings would speak for a wind superimposed on star-forming regions. A skew toward the blue would hint at outflows on the near side. A skew toward the red would hint at inflows or at dust geometries that mask the near side. Given the current blue continuum and scant dust blue wings are the expectation if winds dominate. Another possible witness is the ratio of forbidden to recombination lines. In shock-dominated zones, forbidden lines of oxygen and sulfur can rise relative to hydrogen lines. In photoionized zones around hot stars, hydrogen can keep pace. If the future spectrum shows enhanced forbidden to recombination ratios alongside blue wings, the wind and shock story will gather weight. The dynamics also carry consequences for the galaxy's mass budget. If outflows are strong, they can expel a significant fraction of the freshly enriched gas before it anchors into new stars, delaying the growth of a long-lived metal-rich population. That delay would keep the continuum blue for longer and sustain high electron temperatures, preserving the conditions that make oxygen lines bright. In this view, the galaxy alternates between brief bursts that enrich and blow out, and quieter intervals when cooled gas falls back or fresh inflow replenishes the core. The observed compactness suggests that the current phase is near the peak of a burst. The next phase may be a partial quenching by its own breath. Such cycles have been invoked in models of early assembly to explain how small systems can punch above their mass in ionizing power while remaining metal poor in their average stars. They also offer a channel to spread oxygen into the intergalactic medium, early seeding future generations beyond the first islands of light. A final dynamic thread is the possibility of inflow along a cold filament, hinted at by the slight asymmetry and by the need for sustained fuel. Inflow and outflow can coexist with gas streaming in along narrow lanes, while hot winds escape through different windows. That coexistence can boost the apparent ionization by feeding the core while keeping enough low-density paths open for photons to flee. It would also explain how a very young system maintains such a high surface brightness without exhausting its gas instantly. The dance of inflow and outflow is therefore not a contradiction. It is a portrait of balance at the edge of the possible. The present evidence cannot yet separate these threads with numbers, but it draws the outline convincingly. A compact, clumpy starburst at extreme distance likely drives winds that are beginning to carve a halo and to launch a faint tail. Those winds help oxygen become visible and help light escape into a local bubble that thins the fog of the early universe. They may also carry the first chemical exports into the wider web, setting the stage for galaxies not yet born. In this way, dynamics are not garnish. They are the means by which an idea about early oxygen turns into a mechanism, and by which a single object becomes a participant in the rionization of everything. The idea of a local rionization bubble now steps forward, because the visibility of ancient light depends not only on what happens inside a galaxy, but also on what the surrounding hydrogen chooses to do. At a redshift near 14, the wider cosmos is still heavy with neutral hydrogen, a fog that swallows ultraviolet lines and clips the bluest edge of the continuum. Yet the spectrum of JADES-GS-z14-0 shows a clean break, and a blue slope redward of that break, and the colours hint that strong lines may stand high when instruments reach the right wavelengths. These facts together suggest that the galaxy does not live in an entirely opaque sea. Instead, it may sit inside a small region, where hydrogen is already ionized, a transparent pocket inflated by hard light, leaking from clustered stars and perhaps by the energy of shock fronts. Such a pocket would act like a local clearing in a misty valley. Inside the clearing, light runs freely. At the edge, the fog thickens and reshapes features that try to pass. The size of this bubble depends on three linked things: how many ionizing photons the galaxy produces, how many of those photons escape its knots and cavities, and how quickly surrounding gas recombines once it is torn apart. The images and spectrum already speak to the first two. A very blue continuum and compact clumps point to many massive short-lived stars, and to a porous geometry that lets light find paths outward. The third factor, the rate at which electrons and protons reunite in the neighbourhood, depends on density and on clumping outside the galaxy. In a young region, just finding its shape density is uneven. Some pockets resist and stay neutral longer, while others thin out under the push of heat and radiation. The result is a bubble with a ragged edge, and a preference for growth along the easiest routes. If such a bubble surrounds JADES-GS-z14-0, it would help explain why the continuum redwood of the hydrogen break is present and steady, and why a lingering damping wing near the position of the hydrogen Lyman alpha line may be only a hint rather than a wall. The physical picture is not only a matter of one galaxy's power. A bubble grows faster and lives longer when neighbours also contribute. The deep field that holds the source is peppered with tiny candidates that almost slip below detection, and though most are too faint to characterize their mere presence, raises the chance that clustered efforts are at work. A few faint companions at slightly lower redshifts could be older members of the same rising structure, while even fainter ones at similar distance could be peers feeding the local clearing with their own trickles of hard light. Together they would lower the demand on any single engine. The compact size of the main source, its high star formation surface density, and the vigorous ionization implied by the colours mark it as a likely leader in this small alliance, a lantern held high, while smaller lamps add their glow. The bubble narrative influences the reading of emission lines as well. In a thick neutral sea, even narrow lines can be broadened and dimmed by scattering at the edge of the bubble, and some lines fail to escape at all. In a clearer local region, lines travel farther before they meet the fog, and so their shapes remain closer to the forms made at the source. For doubly ionized oxygen in the mid-infrared, the main risk from the outside fog is not absorption, but competition with background and instrument noise. For the hydrogen Lyman alpha line in the ultraviolet, the fog is decisive. A small bubble can still clip the line, while a larger bubble can let a redshifted wing slide out. The tentative softness just redward of the expected position in the current spectrum may be the fingerprint of this edge. If later data confirm such a signature, they will offer a measure of the bubble size and a check on escape fraction, because the line shape balances the speed of light's exit against the thickness of the boundary. The story widens further when the bubble is set against the timeline of global reionization. If local bubbles like this are common at such early times, they may be the first seeds of a network that soon grows and links, turning isolated clearings into continuous avenues of transparency along the forming cosmic web. If they are rare, then JADES-GS-z14-0 becomes a hard case that proves a possibility that under the right combination of compact structure, clustered stars, scarce dust and porous gas, a single small system can push back the fog ahead of schedule. Either way, the existence of a bubble shifts the view of how and where the earliest oxygen lines could be seen. It says that line visibility is not only a property of the source, but a property of its environment that changes from place to place. A practical test of the bubble picture is to look for a gentle step in the density of nearby faint sources, a bias that marks an early node of the cosmic web. Another is to search for small correlated variations in the background just outside the galaxy, a sign that photons have heated the neighborhood. Far infrared cooling lines from the halo, if detected by the Atacama Large Millimeter Array, would also speak to gas that has been warmed and thinned. A complementary test lies in the mid-infrared line ratios measured by the mid-infrared instrument. High ratios of doubly ionized oxygen to hydrogen beta would fit a hard, leaky engine. Lower ratios with broader profiles would speak more for shocks and for an edge where scattering still matters. The bubble has a cost as well as a gift. Light that escapes into space to carve a clearing is light that does not ionize nearby gas that would otherwise glow in lines. A very high escape fraction can therefore lower local nebula brightness, even while it eases the path for the photons that survive. The current photometry seems to point to a middle state, where enough light escapes to keep the neighborhood clear, yet enough remains to power strong lines in dense pockets. That balance is fragile and likely time-dependent. As the burst ages and as winds widen the channels, the escape fraction may rise, the local glow may peak, and then fade, and the bubble may grow until it meets the next clearing. In that meeting, the early map of reionization takes shape not as a smooth tide, but as a quilt of growing patches that finally merge. JADES-GS-z14-0 by this reading is a small but assertive needle threading one of the first squares. The closing lesson of the bubble is humility and ambition at once. Humility because a clear view of one galaxy may be a gift of its environment, not only of its inner strength. Ambition because a single compact starburst can take hold of that environment and reshape it quickly. The earliest oxygen, if soon measured directly, will not only tell of stars and gas within a quarter of a kiloparsec, it will also tell of a young uneven universe that allows light to cut windows sooner than once thought windows through which we now peer back, watching the first beacons learn to both shine and clear the way. Crosschecks now define the work because a claim that oxygen rises at such distance must withstand not only technical questions, but also the habits and philosophies of different teams. The object's imaging and spectrum are distributed to independent analysts within the James Webb Space Telescope Advanced Deep Extragalactic Survey and to collaborators outside the core group. Each team builds its own pipeline from the raw frames upward, beginning with bias removal and dark current subtraction for the near-infrared camera and the near-infrared spectrograph, and then moving through flat field corrections, bad pixel maps, and cosmic ray rejection. The dithers and nods are treated with separate alignments and with distinct rules for outlier clipping. Where one group favors conservative masking near bright neighbors, another allows a looser boundary to capture more of the faint outskirts. The result of these choices is compared at every stage. Photometry measured in matched apertures recovers the same blue continuum and the same elevated red filters that first raise suspicion of oxygen. Spectra extracted with different tracing methods recover the same clean hydrogen break. The agreement is not perfect at the level of small numbers, but it is stubborn at the level of meaning. Calibration is the second arena. 0 points for the near-infrared camera bands are red-derived from standard stars in the field and checked against catalogued standards elsewhere. The differences are small and when applied shift the entire spectral energy distribution by only a few hundredths of a magnitude in most filters. These shifts are too modest to erase the elevated points or to turn the blue slope into a red one. Wavelength calibration for the near-infrared spectrograph is audited using lamp lines and field stars. The spectral break falls at the same place within a small fraction of a resolution element across reductions. Persistence, latent images, and scattered light are hunted by inspecting the sequence order and by comparing frames taken at different roll angles. Frames that show even a hint of contamination are removed, and the answer does not change. The object remains a distant compact source, whose colours insist on strong lines at wavelengths beyond the reach of the present spectrograph. A different class of cross-check treats the possibility that the entire conclusion is a subtle artifact of how models meet data. To confront this, the teams employ blind injections. Synthetic galaxies are painted into the raw exposures with known properties that span a range of redshift sizes, dust levels, and line strengths. These synthetic skies travel through the same detection and measurement steps as the real field. When the recovered catalogues are fit without knowledge of which sources are synthetic, the pipelines that find JADES-GS-z14-0 at very high redshift also recover the injected high redshift cases and reject the low redshift imposters that mimic colour, jumps with dust and extreme lines. False positives do occur, but their rate falls sharply once size continuum slope and the spectroscopic break are all required together. The real object sits in the region of parameter space where true high redshift sources congregate in these tests. An additional check splits the data by time and by orientation. Photometry measured from half the exposures and then from the other half returns consistent colours within the uncertainties. Spectra built from alternating frames show the same break and the same absence of distracting features. A jackknife test that removes one exposure at a time yields no single frame whose presence or absence alters the redshift solution. These simple but ruthless cuts matter because fragile answers often break under such a tension. Here they do not. The modelling step is then diversified. Instead of relying on one library of stellar population and nebula templates, the teams use several ranging from fast empirical sets guided by galaxies at lower redshift to physically motivated grids that allow very young bursts, very low metallicity, and a span of ionization parameters. Some groups use fully Bayesian samplers that return posterior distributions over redshift age mass metallicity and dust. Others favour nested searches that map likelihood ridges without heavy priors. The favoured solution remains at very high redshift with minimal dust and with line power that suggests oxygen. Low redshift alternatives require a contrived combination of an old stellar break, very strong lines landing in narrow windows, and enough dust to redden the continuum without overshooting the observed slope, a balancing act that refuses to hold once the spectroscopic break is introduced. The teams also test the sensitivity of the conclusion to geometry. Smooth light profiles, two-component fits, and clumpy arrangements are all considered when converting aperture fluxes into total fluxes. The compact size helps here. The source is resolved but only slightly, so reasonable choices for profile shape do not swing the integrated brightness enough to alter the interpretation. In the spectrum, different background models are tried, including backgrounds built from neighbouring shutters, from averages over empty shutters across the field, and from polynomial fits along the spatial direction. The break survives all of these and the faint continuum redwood remains. External constraints are folded in with care. The Atacama Large Millimeter Array reports limits rather than detections on dust continuum and on far infrared cooling lines. Those limits are translated into caps on dust mass and on dense neutral gas. They do not disprove the oxygen picture. Instead, they pressure the models toward hot-low dust and high ionization, states a pressure that agrees with the blue continuum and the elevated filters. The teams verify that these limits are not being misread by reprocessing the public interferometric data with independent pipelines. The limits hold. A complementary cross-check samples the neighborhood. Faint sources around the galaxy are catalogued and their colors and shapes are examined for signs of a common environment or for lensing patterns that might magnify the object. No arcs, no mirrored pairs, no sheared ring appears. The nearest candidates are tiny and blue, likely separate small systems. Their presence favors a young node of structure, but they do not demand magnification or blending to explain the main source. Finally, the human element is given room. Teams meet and present their reductions without showing their preferred conclusions until the end of each session. This practice forces the discussion toward methods and away from outcomes. When the results are revealed, the convergence is striking. Differences in small numbers persist as they should, but the story remains the same. A compact, clumpy galaxy at a redshift near 14 exhibits colors that imply strong lines from oxygen and hydrogen at mid-infrared wavelengths, and a spectrum that anchors the distance with a clean break. Agreement grows, but so does unease, because agreement cannot by itself resolve the tension, with timelines that prefer slower enrichment. The more the data are trusted, the more the clock seems to rush. The cross-checks, therefore, do not end the mystery, they deepen it. They move uncertainty from the realm of measurement to the realm of physics where it belongs, and they sharpen the next questions. How many such galaxies exist at this early time? How quickly do their bubbles grow and meet? How often do their bursts repeat? With methods now harmonized, the teams turn to the plan that will either clinch or complicate the oxygen, story, direct line measurements with the mid-infrared instrument, and a deeper search for far-infrared whispers with the Atacama Large Millimeter Array. The moment arrives to weigh competing explanations not as a contest to crown a winner, but as a tour through possibilities that each illuminate a different path to early oxygen. The first and most conservative path is a dense young cluster model. In this view, the galaxy is a compact city of star-forming knots, where gravity and gas meet in a very small volume. Massive stars dominate the light because the burst is very young, the continuum stays blue because dust has barely formed, and the radiation is hard enough to doubly ionize oxygen. The strengths here are clear. This model fits the size, the blue continuum, the high surface brightness, and the clumpy morphology. It also agrees with the way clustered feedback can carve porous channels that raise the escape fraction and help a local ionization bubble grow. The weakness is time. To place oxygen at modest abundance so early, the loop of star birth, death, and mixing must be swift. The model answers with overlapping supernova remnants that stir the gas quickly, but critics point to the sheer pace required when the universe is only a few 100 million years old. The second path leans on a rapid supernova cycle. Here the first generation of massive stars has already exploded, and their ejecta permeate the small system in a matter of a few million years. Shock fronts double as both enrichers and ionizers, adding hardness to the radiation field and lifting the oxygen lines beyond what stars alone would do at the same metallicity. This route relieves the timeline by letting enrichment and ionization advance together. It also gives a role to the faint tail as a possible wake of recent energy. Yet it introduces new tensions. Shocks can boost forbidden lines relative to hydrogen lines, and can broaden profiles in ways that later spectra must test. If the future mid-infrared lines show narrow cores without wings and hydrogen lines that keep pace, the shock emphasis will have to soften. The third path suggests a tilted distribution of stellar masses toward the very massive. A top-heavy birthless raises the number of hot giants per unit mass of stars, accelerates the arrival of the first supernovae, and floods the gas with hard photons. In this picture, the galaxy does not need to be more efficient. It simply spends more of its star formation on the hottest engines. The gains are obvious. The continuum remains blue. The line power rises and enrichment comes fast. The costs are subtle. A very top-heavy distribution changes many observables at once. Helium lines should strengthen relative to hydrogen. Nitrogen behavior may shift as secondary production lags. The mid-infrared line ratios will tell whether this balance holds. If the ratios fall into neighborhoods that standard distributions cannot reach without dust or extreme geometry, the tilt grows persuasive. If not, the tilt must relax. A fourth path invokes gravitational lensing, the quiet magnifier that can lift a modest source into prominence without changing its intrinsic properties. Even a small magnification can trick flux limits and make a rare object appear more typical. If a foreground mass amplifies the galaxy, some of the pressure to be extraordinary eases. The images, however, resist this. There are no arcs, no mirrored shapes, and the shear pattern in faint neighbours is blank. Simple models return small magnifications at most. Lensing may be present at a gentle level, but it cannot shoulder the responsibility for the extreme distance and the colours. It remains a footnote, not a fix. A fifth path points to calibration uncertainties. Photometric 0 points can drift flat fields, can harbour quiet scars, and background subtraction can lean on assumptions. If elevated filters are victims of such errors, the case for strong lines would soften. The cross-checks answer this with stubborn agreement across independent reductions, new 0 points, noise realizations, and forward modelling. Small shifts occur as expected, but the elevated points and the blue continuum remain. Calibration can no longer carry the doubt alone. A sixth path imagines a blended interloper, a low redshift emission line galaxy folded beneath a high redshift blue source, their light entangled in one unresolved knot. This would explain strong filters without early oxygen. Tests of shape and residuals after point spread function, fitting find no such companion. Apertures enlarged and rotated give the same flux within uncertainties and catalogues. At other wavelengths do not reveal a plausible foreground partner. Without a second image or a lopsided tail of light, this blend fades as a candidate. A seventh path leans on geometry. If the interstellar medium is a patchwork where hot faces of clumps and cooler interiors mix in the beamline to continuum ratios, can climb without extreme stellar assumptions. Porosity and orientation then become quiet variables that steer the observables. This idea harmonizes with the compact, clumpy morphology and with the need for channels that boost photon escape. Its weakness is that geometry does not enrich. It can amplify signal and reshape lines, but it cannot plant oxygen. Geometry thus serves as a multiplier, not a source. An eighth path raises the possibility of a hidden accretion engine, a central massive black hole feeding on inflow and sending out hard light. Even a small such engine could harden the spectrum and help ionize oxygen. The data at hand do not demand this. The continuum is blue and consistent with stars. The size is small and lacks the core profile often linked with intense nuclei. Future spectra can test for high ionization lines that would betray an active nucleus. In their absence, the hidden engine remains conjecture that solves little, while complicating much. Each explanation tries to pay the bill for early oxygen. Dense clusters pay with pressure and speed. Rapid supernovae pay with shocks and overlap. A tilted mass distribution pays with a change in the character of birth. Lensing tries to pay with an external loan. Calibration tries to pay with an accounting error. Blends try to pay with confusion. Geometry pays with arrangement. A hidden engine pays with an extra power plant. None of these currencies are free of interest. Dense clusters must sustain their intensity without aging too fast. Rapid supernovae must raise lines without overshooting profiles. A tilted distribution must pass the future line ratio exams. Lensing must leave signatures it does not leave. Calibration and blends must evade cross-checks they have not evaded. Geometry must join with a real source of metals. A hidden engine must announce itself or be rejected. The weight of the evidence so far clusters around a hybrid that favours dense young clusters, modest early enrichment, high electron temperatures, porous geometry, and perhaps a touch of shocks. This blend explains the blue continuum, the elevated filters, the compact size, the faint tail, and the need for a local bubble. It leaves room for line profiles and ratios still to be measured. It also carries an implication that matters beyond one object. If such hybrids are common, then the early universe is not a slow simmer, but a set of hotspots where gravity, gas, and youth compress time. If they are rare, they still reveal the edge conditions under which oxygen can appear quickly. The next step is surgical. The mid-infrared instrument will test the ratios of doubly ionized oxygen, to hydrogen beta the presence of helium, and the widths of the lines. The Atacama Large Millimeter Array will listen for far-infrared cooling and for whispering dust. These measures will either tighten the hybrid into a clear mechanism or pry it open into deeper puzzles. Until then, the field holds its breath, because competing explanations have narrowed not into a single certainty, but into a family portrait where every member adds a feature, and every feature points back to the central fact that resists dismissal. Oxygen arrives early, and the universe seems comfortable with that speed. The search for radio echoes begins at a high plateau, where dry air and cold nights turn millimeter waves into carriers of ancient stories. The Atacama Large Millimeter Array trains its many dishes on the coordinates of the compact galaxy, each antenna a patient ear, and together they weave an interferometric net that can hear whispers of cold dust and of far-infrared cooling lines carried to millimeter wavelengths by the stretch of cosmic expansion. The immediate targets are natural: the line of singly ionized carbon at 158 microns in the rest frame, and the line of doubly ionized oxygen at 88 microns each, a standard coolant in gas touched by star formation, each a possible tracer of metallicity density and the behavior of radiation fields. Observing at such extreme distance is a practice in audacity. The lines now live at wavelengths farther by a large factor, and the sky itself hums with a slow, bright background. The array composes long integrations, spreads baselines to balance sensitivity and resolution, and steps frequencies to cover uncertainties in the precise redshift left by the near-infrared spectrum. Calibrators march through the sequence to pin the phases and gains, and the data stream grows thin yet orderly. The reduction that follows is a craft. The visibilities are flagged for radio frequency interference, the bandpass is shaped with bright standards, and the phases are corrected using compact sources near the field. Maps arise from Fourier transforms and then from deconvolution that tries to separate true sky from the pattern of the instrument. The central beam is placed on JADES-GS-z14-0, and off beams are built to gauge the noise. The first message is silence. No bright line leaps from the noise, no broad wing announces a wind, and no obvious continuum glows like a small hearth of dust. This quiet does not kill the story, it sharpens it. Limits are drawn with care, folding in the system temperature, the coverage and the plane of spatial frequencies, and the shape of the synthesized beam. Those limits fall on the expected strength from models and begin to prune them. The absence of a strong continuum argues that the dust mass is small and that grains are not hiding a substantial fraction of the star-forming light. That conclusion agrees with the blue near-infrared continuum and with the idea of porous channels that let photons escape. The absence of a loud singly ionized carbon line lowers the ceiling on the mass of cool neutral gas within the beam and suggests either a low metallicity, a high ionization parameter that leaves little neutral carbon, or a gas temperature and density combination that moves cooling to other lines. The doubly ionized oxygen line at 88 microns is an eloquent but difficult target. In low metallicity, hard radiation and high electron temperature, this line can dominate far infrared cooling. A non-detection therefore cuts two ways. If the line is simply below the threshold, then the conditions may be even hotter and more ionized than expected, moving line power to mid-infrared features. If the line is partly resolved out by the interferometer because the emission smears across scales larger than the array is tuned to here, then the non-detection hints at a diffuse halo of warm ionized gas rather than a compact core alone. The team tests both ideas by reweighting the visibilities to emphasize short baselines that are sensitive to broad structures and by tapering the resolution to gather faint extended light. The maps remain quiet, but the limits soften in a way consistent with emission that is faint and spread. That faintness is not an absence of physics, it is a signature. In a compact, very young galaxy where the hard light is fierce and dust is scarce, a large share of the energy may leave as ionizing photons and as mid-infrared lines, rather than as the far-infrared and millimeter features more familiar at later times. The Atacama Large Millimeter Array also hunts for companions. The field within the primary beam is scanned for narrow lines at the frequencies that the redshift solution would allow, because a nearby faint galaxy may glow where the main source only whispers. Such a companion could be a member of the same young node of structure contributing to a shared ionized bubble. A few hints of narrow features at the edge of significance appear and then fade under stricter cuts. The conclusion remains that if companions exist, they are too faint for this pass to reveal. The work then turns to stacking. All channels that could host the singly ionized carbon line within the redshift uncertainty are aligned and coded. The same is done for the doubly ionized oxygen line. Stacking erases noise like a tide erases footprints, but it cannot conjure signal where none exists. A small crest rises in the stack of the oxygen line below the usual threshold for a claim, but high enough to tease. The team records it as a hint to be tested by deeper time. Even in silence, the array gives numbers that matter. From the continuum limits, an upper bound on dust mass is derived under reasonable assumptions for grain temperature in a starburst of this kind. That bound fits the picture drawn by near-infrared colors and by the lack of mid-infrared rise in the existing photometry. From the line limits, bounds on gas density and metallicity are drawn using grids of cooling models. Those bounds prefer a regime where oxygen exists, but where the fraction of neutral gas is small within the beam, a match to a porous bubble carving interior. A further inference comes from the non-detection of a wide, powerful line that would betray an outsized wind. Winds may be present and likely are, but they are not dumping enough dense, cooled, high-column gas into the beam to shout at millimeter wavelengths yet. If they are there, they are hot or they are thin, and they may be mixing faster than they condense. Sensitivity to these edges improves with time and configuration, and the team schedules future sessions with even shorter baselines and with deeper integrations. They also explore complementarity with the mid-infrared instrument. If mid-infrared oxygen and hydrogen lines appear strong, while far-infrared cooling lines remain modest, the balance will confirm the idea that the gas is hot, the ionization high, and the dust scarce. If conversely deeper millimeter work later reveals a diffuse doubly ionized oxygen line spread across many kiloparsecs, It will mean that early feedback has already filled a halo with warm ionized material, and that the invisibility of the line today was a matter of sensitivity and scale. The Atacama Large Millimeter Array thus acts as a judge in a case where absence is evidence. It does not condemn the oxygen story, it corrals it. It says that if oxygen is abundant, it lives in a state that favours mid-infrared brightness over far-infrared comfort, and that the dust which might have hidden light is too little to matter much. It says that cool neutral gas is not yet dominant, or that if it is present, it is spread so thin that even a field of large dishes cannot pull it from the noise with current time. This guidance shapes the next campaign plans. The mid-infrared spectra will aim with more confidence, and the millimeter maps will reach for larger scales and finer sensitivity. In the meantime, the quiet from the plateau becomes another thread in the tapestry. It matches the blue continuum, the compact clumps, the likely high electron temperature, and the notion of a small ionized bubble. Radio echoes are faint here, but faint is not a failure. It is a clue that the factory of oxygen glows in heat and hardness, rather than in the soft comfort of abundant dust and cool clouds. The early universe in this corner remains a clear room where light runs far and metals are young. Models now bend to the data, and in that bending they reveal where understanding is stiff and where it is supple. Teams take cosmological simulations that usually describe the slow rise of small galaxies and begin to change the rules in careful steps. Gas inflow rates are raised along narrow filaments. Cooling is allowed to proceed faster at low metallicity, and star formation thresholds are adjusted so that dense pockets ignite in bursts rather than in long calm seasons. Feedback recipes that govern how supernovae and stellar winds deposit energy into gas are rewritten to overlap more carving porous channels earlier in a galaxy's life. Escape fractions that control how easily ionizing photons flee their birth clouds are nudged upward in compact systems. With these changes, simulated galaxies at ages of only a few 100 million years begin to look more like JADES-GS-z14-0. They become compact and clumpy. Their rest frame ultraviolet light turns very blue, and their nebular line predictions climb, especially for the doubly ionized oxygen features that would lift, broad filters in the near-infrared and sing in the mid-infrared. The successes are real, yet each one comes paired with a new imbalance. When gas inflow is raised to feed rapid bursts, the total stellar mass grows faster than some counts of early galaxies allow, unless feedback throws much of that gas back out. When feedback is strengthened to hold masses in check, line emission can fall unless geometry remains porous and clumps stay dense, a combination that is hard to sustain for long. When escape fractions are raised to build local ionized bubbles. The nebular glow inside the galaxy can fade if too many photons leave, and the predicted fair infrared cooling lines can drop below limits that are already tight. To keep both a strong local glow and a clear environment, the simulation must find a moving middle ground in which the earliest cavities open, but do not yet drain the engine. A different set of changes explores the distribution of stellar masses at birth. If the first bursts form more very massive stars than later bursts do, the hard radiation field strengthens and the first supernovae arrive quickly. This tilt raises the doubly ionized oxygen lines and accelerates enrichment toward the modest metallicities that the data seem to like, yet it also shifts helium and nitrogen behavior and can make the continuum even bluer than observed. When dust is scarce, as the blue slope suggests, there is little room to hide such excess. The model therefore learns to tilt only modestly, and only for short windows, something like a switch that flips during the densest episodes and then relaxes. The price of this finesse is fine-tuning. Nature may accept such switches if they emerge from simple causes like pressure and crowding in gas, but simulators remain wary of turning dials that lack clear physical handles. Geometry emerges as a quiet savior across many runs. When star formation is forced to clump and to migrate within a very small region, overlapping Strömgren zones and shock cavities produce a mosaic of hot faces, thin channels, and cooler interiors. The integrated light from such a mosaic can raise line to continuum ratios without invoking extreme metallicity or extreme tilt in stellar masses. It also builds the local ionized bubble more naturally, because clustered cavities join into a clearing that favors escape along a few paths while still leaving dense pockets lit from within. However, this same geometry can create flicker. As clumps move, collide, and dissolve the brightness of lines, and the escape fraction can change on timescales of only a few million years. This flicker offers a prediction that observations can test if the field holds several similar sources. Their line strength should vary widely for the same continuum slope and size, not because their mean properties differ, but because each is caught at a different phase of the same cycle. The Atacama Large Millimeter Array limits slide into the models as a stern teacher. Runs that produce large masses of cool neutral gas and bright far-infrared cooling lines are now discouraged. The favored region of parameter space keeps the gas hot ionized and porous, with dust masses that are low enough to fall below current limits and with far-infrared lines that are modest. The mid-infrared instrument predictions in contrast rise. Doubly ionized oxygen and hydrogen beta should be bright, relative to the continuum with widths that show narrow cores and mild wings, if winds are present but not yet dominant in dense cool gas. Helium lines should appear at levels that distinguish modest tilt in stellar masses from none, and ratios among oxygen states should mark a high ionization parameter. A further lesson from the rewrites concerns the pace of enrichment. In runs that match the blue continuum and the compact size, the first oxygen appears in only a few million years after the first giants die, and mixing across a region a few hundred parsecs across occurs in of order 10 million years when clusters overlap. These numbers are uncomfortable to some, but they are not absurd. They flow from simple facts. Small distances, high densities, and crowded events shorten clocks. What remains controversial is how often such clocks run so fast across the early universe. If simulations turn the necessary knobs everywhere, they overproduce bright, compact sources by redshift counts. If they confine the knobs to rare peaks, they match counts, but risk making JADES-GS-z14-0 a statistical fluke. The compromise that emerges is environmental. Early nodes of the forming cosmic web, where several thin filaments meet, receive above-average inflow and build above-average pressure. In those nodes, the necessary conditions arrive together more often, and the fast clocks run. Elsewhere, the pace is slower. This compromise suggests a test that reaches beyond one object. A field that contains a galaxy like JADES-GS-z14-0 should show a mild excess of other tiny blue sources in its larger neighborhood, even if they sit below many detection thresholds. Stacked signals and weak clustering should betray the node. If such signs appear, the fast mode is a feature of environment rather than an unfair dial. If they do not, the models must learn a more global path to speed. Finally, the rewrites teach humility about the inner gravitational core. Runs that match the observed outer features still diverge near the center. Some grow a dense central mass that could one day feed a massive black hole, while others remain a swarm of massive clusters without a single ruler. The present data do not decide between these futures. They do, however, encourage a view in which gravity, pressure, and radiation cooperate rather than compete, building a center that is complex rather than monolithic. The models leave the stage with predictions written plainly. Mid-infrared spectra will show strong doubly ionized oxygen and hydrogen beta with high ratios that mark a hard field. Helium will appear but not overwhelm. Line cores will be narrow with gentle wings. Far infrared lines will be faint or spread. Dust will be scarce and hot if present at all. The field will host other faint blue neighbours. If these predictions land, the rewrites will have moved from accommodation to understanding. If they miss, the next bend will be sharper, and the mystery will thicken. The galaxy at a redshift near 14 thus forces theory to run, and theory in running learns where the ground is smooth and where it hides stones. The gaze now narrows to the inner gravitational core, a region only a few hundred parsecs across, where light matter and motion negotiate the identity of the young galaxy. Gravity in so small a volume is not gentle. It is a steep well that gathers clumps, bends, orbits, and drains angular momentum through tides and torques when bright knots pass and tug on one another. In such places, star-forming clumps do not keep to tidy rings. They migrate inward like rafts on a river that deepens toward its source. Each inward step concentrates mass and raises pressure, and each new crowding event lights a fresh burst that reinforces the cycle. The inner profile glimpsed in the images suggests a dominant central knot, with a faint extension, a head and a tail balanced on a tight curve of potential. If the tail marks an inflow lane, then gas is being funneled toward the core along a path carved by gravity and then polished by feedback. The clumps that ride this lane carry both fuel and metals. When they collide and merge near the centre, they thicken the reservoir of gas, trigger more massive bursts, and fold the first oxygen into the core where winds then try to lift it outward again. The result is a churn, not a conveyor belt, a feedback loop that sends enriched gas outward along some lines, while drawing fresher gas inward along others. In this churn, the idea of a single ruler becomes complicated. A dense nuclear star cluster can grow in such a setting if migration and merging proceed quickly. Its gravity would hold the brightest stars in a compact ball, and would imprint subtle signatures on future line widths, narrow cores with slight wings from the orbital speeds in the inner few tens of parsecs. A different outcome is the rapid assembly of a seed for a massive black hole through runaway collapse in a gas-rich core where cooling is fast and turbulence is strong. The present data do not require such a seed, and the continuum looks stellar rather than nuclear, but the pressure and inflow environment make the possibility natural rather than exotic. If a seed exists, it is small and quiet, adding hardness only at the margins, yet it could shape the inner geometry by heating and stirring gas on scales too fine to resolve. The visible engine remains the clustered stars. Their radiation hollowed the first cavities, and their supernova built the first hot bubbles that now knit into the local ionized pocket. Inside the core, their winds and shocks peel away low, density skins from denser knots, exposing hot faces that dominate the emission. Those faces are where oxygen lines would blaze brightest once the wavelengths are reached. They sit at the interface where pressure radiation and gravity meet, and they move on timescales of only a few million years, so the core is not a still portrait. It is a sequence captured mid-frame. Angular momentum is the quiet currency that pays for this sequence. To fall inward, gas must shed it, and the easiest way to shed it in so small a system is through gravitational nudges when clumps pass, and through asymmetric outflows that remove momentum with mass. The faint tail could be part of that account book, a subtle sign that the core is trading mass and momentum with its outskirts. If so, the inner region is learning to regulate itself, tightening during bursts and then loosening as winds relieve the pressure. Such regulation keeps the continuum blue by preventing a rapid build-up of old stars, and it keeps the electron temperature high by allowing new hot faces to keep replacing those that cool. The inner potential also decides how far oxygen can travel before it either escapes or returns. If winds clear narrow chimneys, some enriched gas may leave the core but stall in the shallow halo, ready to rain back during the next inflow episode. That fountain would mix metals across the central few hundred parsecs, quickly helping the observed modest metallicity appear uniform from the outskirts to the center without demanding an improbable diffusion speed. In a stronger wind, oxygen would fly beyond the halo and seed the neighborhood, but the lack of loud, far-infrared cooling lines suggests that dense cooled outflow has not yet piled up on large scales. The balance therefore tilts toward recycling within the core, and its near halo, a loop that can run several times before the next stage of growth begins. A test for this picture lies in the relation between line widths and sizes once mid-infrared spectra arrive. If the inner knot rules, widths should scale with the compact size and show a gentle increase toward the center. If a hidden seed is adding gravity, very inner widths may rise above the stellar prediction. If instead the core is a swarm without a single ruler, widths will be set mostly by turbulence and by overlapping shells, and profiles will show mild asymmetries rather than a clean central rise. Another test is the ratio of helium to hydrogen lines. A central cluster biased toward very massive stars raises helium relative to hydrogen, while a calmer cluster does not. That ratio will tell whether the core prefers extreme engines or a vigorous but standard mix. The gravitational heart also sets the pace of the local reionization bubble. A deeper core stabilizes the central gas enough to keep bursts repeating, while a shallower core allows single events to blow out more of the reservoir and pause the cycle. The images and spectrum argue for repetition rather than a single passed burst of verdict that favors a core deep enough to contain its own weather. Containment here does not mean quiet. It means coherence, a tendency for the pieces to argue and agree along shared lines rather than to fly apart. That coherence appears in the alignment of the head and tail, in the persistence of the blue slope across apertures, and in the stubborn survival of the elevated filters under many reductions. The inner gravitational core is therefore not a hidden monolith but a conductor. It does not write the notes, it sets the tempo. Gravity conducts the inflow, feedback keeps the percussion, radiation carries the melody, and oxygen provides the early harmony that should with the right instruments resolve into measurable chords. Whether a compact nuclear cluster, a nascent seed, or a swarm of clumps holds the baton, the performance at this early time has already reached a loudness that earlier histories did not expect. The final question is not whether oxygen is present in the inner heart, but how the heart learned the rhythm so quickly. Perhaps the answer is simple scale. Short distances, high densities, and narrow lanes allow cycles to close in only a few million years. Perhaps it is environment. A small node on the newborn web funnels fuel and raises pressure beyond the average. Perhaps it's a brief tilt in how stars are born under such strain, a temporary favouring of the giants that end fast and enrich hard. The core keeps its counsel for now. Its gravity is obvious, its light is blue, its features are compact and its implications are large. The next measurements will breach the wavelengths where oxygen lines wait, and the heart will either confirm that it already beats with metal or will force a deeper revision in how the first conductors learned their craft. Either way, the core stands as the place where the earliest chemical history becomes not an inference from colour, but a map drawn by lines, a map that will tell how the first furnaces were arranged and how quickly they learned to burn. The field dims, and what remains is a gentle afterimage of a compact galaxy breathing in a young universe. Its light crosses almost the whole of cosmic time to arrive, carrying the mark of a clean hydrogen break, and the hint of lines that promise oxygen waiting at longer wavelengths. The picture is small but insistent clustered stars in a tight core, a faint tail that suggests motion, a continuum so blue that dust feels absent, and a pressure so high that ionizing photons likely flee along channels carved by overlapping winds. The tail that forms is not a proclamation but a steady tracing of causes. If oxygen is already present, it is because short lives ended quickly and seeded the gas, because shock fronts added heat and geometry offered thin paths, because inflow fed the core even as outflow cleared it, and because the surroundings yielded a pocket of ionized space where ancient light could run. Nothing here claims a grand exception to nature. The galaxy looks like a familiar mechanism run at its limit, as if gravity, density and youth have compressed the usual sequence into a smaller stage and a faster tempo. That compression softens the fear that early metals demand miracles. It trades miracle for urgency. It says that a quarter of a kiloparsec can hold a city of furnaces, and a few million years can hold several rounds of birth and death, and a small bubble can make a window onto the rest of time. Instruments that listen deeper in the mid-infrared and in the millimeter will decide how sharp this outline becomes, whether doubly ionized oxygen sings with the expected strength, whether helium and hydrogen keep the ratios that mark a hard field, whether far-infrared cooling is faint because the gas is hot and porous. Until then, the afterimage lingers. It is a calm shape against a wide darkness, a reminder that the first pages of chemical history are written close to the edge of seeing by galaxies that speak softly and act quickly. Somewhere within that compact core the earliest furnaces still glow and the young bubble still widens and the first metals still learn to travel,